Today's topic is execution cycle. The control unit generates the control words that fetch and execute each instruction. While each instruction is fetched and executed, the computer passes through different timing states known as T states. These T states are periods during which register contents change. Ring counter produces this 6-bit word T equal to T6, T5, T4, T3, T2, T1. At the beginning of computer run, the ring word is T equal to 000001. That is, T1 is 1 and other bits are 0. Successive clock pulses produces these ring words, in which this one shifts from right to left, and we have these 6 T states. In first T state, T1 is 1, other bits are 0. Next T state, T2 is 1, other bits are 0, and so on. Out of these 6 T states, first 3 T states are fetch cycle and last 3 T states are execution cycle. Last 3 T states, T4, T5 and T6 states, are the execution cycle of sap-1. The register transfers during the execution cycle depend on the particular instruction being executed. For example, Lda 9H requires different register transfers than add BH. These are two different instructions, Lda 9H and add BH. So these requires different register transfers. Control routines for different sap-1 instructions are as follows. First of all, we will discuss Lda routine. There are 5 instructions for sap-1: Lda, add, sub, out and halt. So we consider first the Lda routine. Lda means load the accumulator. At the end of fetch cycle, the instruction register has been loaded with Lda 9H. Instruction register IR equal to 00001001. The left side 4 bits are operation code for Lda, load the accumulator, and the right side 4 bits are for 9. 9H means 9 in hexadecimal number system. It is equivalent to 1001. So instruction register have this 8-bit word. First left side 4 bits is operation code for Lda, that is 0000, and next right side 4 bits are equivalent to hexadecimal address 9H. It is binary number of 9. During the T4 state, the instruction field 0000 goes to the controller sequencer. This is IR, instruction register, containing this 8-bit word. Zero 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 1001. Out of these 8 bits, 4 bits goes to CON, controller sequencer, and 4 bit goes to this W bus. From instruction register, 4 bits goes directly to controller sequencer CON, and 4 bit goes to this W bus, and these 4 bits which goes to W bus, this happen when EI bar is active. EI bar, E for enable, I for instruction register. When EI bar is active, then these 4 bits goes to W bus from IR, instruction register. During the T4 state, the instruction field 0000 goes to the controller sequencer, and the address field is loaded into the MAR. Left side 4 bits are instruction field and right side 4 bits are address field. Instruction field goes to CON, controller sequencer, and address field is loaded to MAR. So to load instruction field to MAR, first of all these 4 bits from IR must go to W bus, and this happen when EI bar is active. Then 4 address field bits goes to W bus, and from W bus these 4 address field bits are loaded to MAR. This happens when LM bar is active. Load MAR. So in this T4 state, these MAR, memory address register, IR, instruction register, and CON, controller sequencer, these are active, and all other parts are inactive. Figure 1a shows the active parts during this T4 state. EI bar and LM bar are active during this state. Controller sequencer produces a 12-bit control word, and out of these 12 bits, only these 2 bits must be active, LM bar and EI bar. EI bar, when EI bar is active, 4-bit words goes to W bus, and that 4-bit word goes to MAR when LM bar is active. During the T5 state, CE bar and LA bar bits are active. CE bar is connected with RAM, memory, and LA bar is connected to accumulator, that is A register. This loaded the accumulator with the addressed data word in the RAM on the next positive clock edge. So we have to load the address data word which is stored in the memory RAM. We have to load it into the accumulator. So from MAR 4 bits goes to RAM directly, where the word contained in memory location 9H is read, and when CE bar is active, that word goes to W bus. So we have to load this accumulator by the content of memory location 9H. The word in memory location 9H is stored in this RAM, and when CE bar is active, chip enable is active, that word goes to W bus, and from W bus that word goes to accumulator when LA bar is active, load accumulator, L for load, A for accumulator. So when CE bar is active and LA bar is active, the word in memory location 9H goes from memory, that is RAM, to accumulator A register. This is T5 state. In this T5 state, these parts are active: MAR, RAM, IR, CON, and A accumulator. And active bits are CE bar and LA bar. This loaded the accumulator with the addressed data word in the RAM on the next positive clock edge. T6 is a no operation state. During this state, all registers are inactive. This is the T6 state. All parts are inactive. These are different T states: T1, T2, T3, T4, T5, T6. T1, T2, T3, these three T states are for fetch cycle, and for execution cycle in the T4 state, we see that active bits are LM bar and EI bar. In T4 state, LM bar and EI bar are active. It means LM bar must be 0 and EI bar must be 0. So in this T4 state, we see that LI bar EI bar and LM bar. This is LM bar. It is 0 in T4 state. LM bar. And next is EI bar. This is EI bar, and it must be 0 in this T4 state. This is T4 state, and this is EI bar, that is 0. So in T4 state, EI bar is 0, that is active, and LM bar is 0, that is active. All other bits must be inactive in T4 state. In T5 state, CE bar and LA bar must active. It means CE bar must be 0 and LA bar must be 0 in T5 state. This is the T5 state. CE bar and LA bar. This is CE bar and it is 0 in T5 state, and this is LA bar which is 0 in this T5 state, and in T6 states all bits must be inactive. So this is fetch and LDA timing diagram. Next is add routine. Let at the end of fetch cycle the instruction register has been loaded with add BH. This is add instruction, add BH. It means we have to add the content of accumulator to the content of this hexadecimal address BH. So to add these two words, first we have to load the B register by this content of memory location BH. To add or subtract, we need two words. One word is to be stored in accumulator, A register, and second word is to be stored in B register. First of all, we store the accumulator by first word, by first instruction, that is LDA, load accumulator. And now we want to execute this instruction add BH. It means that we want to add the content of memory location BH to the accumulator word. IR instruction register is now have this 8-bit word. First left side 4 bits are 0001, it is operation code for add, and next 4 bits 1011, it is equivalent to this hexadecimal address B. During the T4 state, the instruction field 0001 goes to the controller sequencer. This is the T4 state. From IR instruction register, which contain 8-bit word, 4 bits goes to CON, controller sequencer. These 4 bits goes directly to controller sequencer, and these 4 bits are the instruction field 0001, which is operation code for add, and the next 4 bits, right side 4 bits 1011, these goes to W bus, and this goes to W bus only when EI bar is active. Enable instruction register, E for enable, I for IR instruction register. So when EI bar is active, when EI bar is 0, these 4 address field bits goes to W bus, and from W bus these 4 bits goes to MAR only when LM bar is active, load MAR. So during T4 state, the active bits are LM bar and EI bar, and active parts are these 3 blocks MAR, IR and CON, controller sequencer. Figure 4 shows the timing diagram for fetch and add routine. No, this is the for T4 state, and during this T4 state LM bar and EI bar bits are active, and these are the active parts MAR, IR and CON. Now during the T5 state CE bar and LB bar bits are active. Now we have to bring the word, the content of memory location BH, which is stored in RAM, which is the memory, and from RAM this word is taken to this B register. So from RAM the word contained in memory location BH is taken to B register. So first of all we have to make this CE bar active. When CE bar is active, chip enable is active, the content of RAM goes to W bus, and from W bus this word goes to B register when LB bar is active, load B register. So active bits in this T5 state are CE bar and LB bar, and active parts are MAR, RAM, IR, CON and B register. All other parts are inactive, that are shown by dark region. So this is the T5 state. Now we have to add the two words which are stored in accumulator A and B register. These two words are added by using this adder subtractor. Accumulator word goes to adder subtractor directly, and the word from B register goes directly to adder subtractor, where these two words from A and B register are added, and this added word goes to accumulator only when EU is active and LA bar is active. When EU is active, this word, which is the addition of A and B register, goes to W bus, and from W bus it goes to accumulator when LA bar is active, load A register. So during this T6 state of add routine, EU and LA bar must be active, so that the content of adder subtractor goes to accumulator A. Active parts in this state are IR, CON and A and B register and adder subtractor. Active bits are LA bar and AU. Now figure 4 shows the timing diagram for fetch and add routine. This is figure 4, which shows timing diagram for fetch and add routine. T1, T2, T3 states are fetch cycle. T4, T5, T6 states are execution cycle for add instruction, that is add BH. During T4 state, active bits are LM bar and EI bar. It means during T4 state, LM bar must be 0 and EI bar must be 0. So this is the T4 state, and is in this T4 state, LM bar and EI bar. This is LM bar, which is 0 in T4 state, and EI bar is here. This EI bar is 0 during this T4 state. During T5 state, the active bits are CE bar and LB bar. These are active when these are 0. So during T5 state, CE bar must be 0 and LB bar must be 0. CE bar is here. This CE bar is 0 during T5 state. And LB bar is here, and this LB bar is also 0 during this T5 state. During T6 state, active bits are EU and LA bar. EU is active when EU is 1 because it have no bar, and LA bar is active when LA bar is 0. All the bits having bar are active when these are 0, and all the bits without bar are active when these are 1. So during T6 state, EU and LA bar must be active. EU is active when EU is 1 and LA bar is active when LA bar is 0. So during T6 state, LA bar must be 0 and EU must be 1. So this is EU and it is 1. Active means EU is 1 during this T6 state, and LA bar is active. It means LA bar is 0 during this T6 state. So these are timing diagram for T1, T2, T3 states which form phase cycle, and T4, T5, T6 which form execution cycle for add routine. Next is subroutine. This subroutine is similar to add routine. Figure 3a and 3b shows the active parts during T4 state and T5 state. During the T6 state, a high SU is sent to adder subtractor of figure 3c. The timing diagram is almost identical to that of figure 4. Visualize SU low during T1 to T5 states and SU high during T6 state. So subroutine is similar to add routine. The T4 and T5 states are same, and during this T6 state, with this adder subtractor we have a bit SU, and that SU is active when SU is 1, then it work as subtractor. So this is change in T6 state for subroutine. Only this, that in this adder subtractor we must have SU active for subtraction. That means SU must be 1 during this T6 state. Next is out routine. Let at the end of phase cycle the instruction register has been loaded with out. IR equal to 1110 XXXX. First left side 4 bits are operation code for out, and right side 4 bits they can be either 0 or 1. whatever they may be. So these are written by X. These are don't cares. X may be 0 or 1. So in out routine, the operation code for out instruction is 1110. During the T4 state, the instruction field 1110 goes to controller sequencer. From instruction register IR, instruction field 1110 goes to CON, controller sequencer. Then the controller sequencer sends out the control word needed to load the accumulator content into output register. So we have to load this accumulator content into the output register. This is loaded. The accumulator content is first loaded to W bus. When this EA is active, enable accumulator EA. A is not shown here, it is not E, it is EA. Enable A register. When EA is active, accumulator word which is stored in accumulator A goes to W bus, and from W bus it goes to output register O when LO bar is active. It is not L, it is LO bar. LO means load output. Then output is loaded with the content of accumulator. It is connected to D display where it is displayed. This is figure 5. It shows T4 state of out instruction. Active parts are IR instruction register, CON controller sequencer, A accumulator, O output register, and D display. And active bits are EA and LO bar. The T5 and T6 states are no operation states. Figure 6 shows the timing diagram for fetch and out routine. The fetch cycle is the same. During the T4 state, EA and LO bar are active. This loads accumulator contents into the output register. So first three states T1, T2, T3 states are of fetch cycle. In the T4 state, the active bits are EA and LO bar. So EA must be 1 during this T4 state and LO bar must be 0 during this T4 state. T5 and T6 states are not needed here. These are no operation states. Last is instruction halt. HLT is for halt. HLT does not require a control routine because no registers are involved in the execution of an halt instruction. When the instruction register contains 1111XXXX, 1111 is operation code for halt. The instruction field signals the controller sequencer to stop processing data. The controller sequencer stops the computer by turning off the clock.